Hi guys, this is Sneaky Nano or Nano. A lot of people wanted to be explained about logarithms, and I was going to do a lecture on it, but everybody didn't really agree on the time. So I decided to start this YouTube channel where I would just explain things like this, and you guys can see my screen obviously. If like this, I should probably make this full screen for you guys. At the end, we'll do some sort of extension for people who want to learn a little bit more, but it's going outside of what we've already learned at this point. So logarithms, I like to think of it as asking a question. A very hard concept to grasp. So if you didn't get it straight away, don't think that you're just dumb or like you're slow at things. You might be, but like, well, this is that. If you are, this is not why. We have 2 squared is equal to 4. Yeah. If I didn't give you this 2, I said 2 to the power of x is equal to 4. You could probably solve this for me and say that x is equal to 2. Because 2 squared is 4, right? No. Or wait, 4 to the power of x is equal to 16. We can solve this just intuitively by looking at it, saying that x is equal to 2 because 4 squared is 16. Sorry for my handwriting. That's meant to be a 16. And again, as we have 2 to the power of x is equal to 8, we can solve this again just using our heads by saying that 2 to the power of 3 is equal to 8, so therefore x is equal to 3. But this isn't always something we can just do in our heads. We can do this in our heads just because we've seen this before, but there's no mathematical thing, any process that we're going through to get to the answer. We're just knowing it just by knowing our multiplications. So for example, if I said that 2 to the power of x is equal to 7, could you tell me what x is here? The answer is probably not. You wouldn't be able to do this in your head, but mathematicians have come up with a neat little function for us to use called logarithms. Logarithms have they actually have 2 inputs. How I like to look at it, but technically they're not inputs. You just have different log functions. What we can also write this as is log base 2. Just what we put down here, 4, is equal to what? So that basically means what power of 2 do we need to get 4? What power of 2 do we need to get 4? Well, the answer to that is 2. You can see that log base 2 4 is equal to 2 since 2 squared is equal to 4. We can do this again. Let's say we have log base 3, 9. Sorry guys. The question that we're asking here is what power of 3 do we need to make 9? And the answer to that is also 2. Since 3 squared is equal to 9. So that's all logarithms are, really. You're just seeing what power of a base you need to make a number. One quick note I wanted to give is that if you just see log and then a number, you assume that this is base 10. And when I say base 10, that means that the number that I said before, what base do we need to make this? The base is equal to 10. So that's the same as log 10, 100. The reason why we default to base 10 is because in our number system, we use denary. And that means that there are 10 digits. 1, 2, 3, 4, 5, 6, 7, 8, 9, and 0. 10 digits. So we call that base 10. This isn't important for logarithms, but I thought it was interesting for you to know where it came from. The reason why we use 10 numbers is because we have 10 fingers. And for us humans, it was intuitive to know that. There's no real reason why log by itself is equal to log base 10. I think it's because we use base 10 the most. So they thought that defaulting to base 10 will make the most sense. But it's just something that you have to accept as something that happens in maths. And by the way, the answer to this is also 2, because we're saying what power of 10 do we need to make 100? We need 10 to the power of 2 to make 100. For logarithms, we have these set rules, and we call these log rules. These are some things that you can apply to logs, and there is a complicated derivation of all these laws, but for me explaining how we get to these laws will just confuse you. It is better to just accept that as something that you need to remember. So our first rule is log A plus log B is equal to log AB, or A times B. By the way, these rules, they only work if the logs are of the same base. So, for example, give me a second, sorry guys. Log 2A plus log 3B is not equal to log, I don't even know what this number would be here, but log AB or whatever. So, because one, it doesn't make sense because you don't know which base to use anyway. So, but anyway, it's not even equivalent. So make sure that these are the same base. If you're doing these for all the rows, they have to be the same base. So we'll apply this by saying the logarithm of 4 plus the logarithm of 5 is equal to the logarithm of 20. And you can type this in your calculator right now. You can't see my calculator. Alright guys, I managed to get my calculator. This is a CG50. Oh god, it's broken. Right guys, I managed to get my CG50 here. And it's the one that I have in real life. It's very expensive, but it's very useful. I'd recommend getting one if you have enough money to, especially for programming. You can do Python scripts and stuff like that on it as well. Anyway, that's my sponsorship from Casio out of the way. So let's see, we got log 4 plus log 5. And we get this. Well, what's 4 times 5? 4 times 5 is 20. So log 20 should give us the same answer. So what we're saying is that log 4 plus log 5 is equal to log 20. That's how it works. The next rule that we have is log A minus log B is equal to log A over B, or A divided by B, as you should know. For example, log 20 minus log 10 is equal to log 2. So example, we can put this in the calculator again, just so you guys know I'm not talking shit, I'm actually telling you the truth. Log 20, I don't know if it thinks it's in the log function still, so I have to do these brackets. We get 0.301 or whatever that is, which should be the same as log 2. See, so we've proven the rule. Well, I haven't proven it, but you can try and do it if you want, but you can see that it works. These rules are just something that you kind of just have to learn. Another rule, a very important one, is if you have a constant, we'll call constant A log B is equal to log A to the B. So for example, if we had 4 log 2, that would be equal to log 2 to the power 4, which is log 16. So it's equal to this. And let's do log 16, which is log 2 to the power 4. And we get the same answer. Look at that. It's almost as if I know what I'm talking about. I'm not lying to you. There we go. We've proven this rule as well. So just to recap, you got this rule here, this rule here, and this rule here. So really that's all that you need to know for logs. One thing I forgot to mention is another logarithm rule that I didn't mention. I forgot it because I don't see it really in questions that often if it's not a maths exam. But I'll go for it anyway because it could absolutely be a question. So I recorded this after the video, but I will put it with the rules. So that's why if you see me sign different, that's probably why. A to the power of log A to x is equal to x. And this one looks header complicated. What the hell is this? What's making it a little bit hard to understand is the fact that we're using letters and not numbers. So if we put numbers in it, it should make it easier to understand. So we have we know that log base 2 4 is equal 2. What power of 2 do we need to get 4? The answer is 2. So that's the same as going 2 log 2 4. And this should equal 4 according to this rule here. So we're saying that a which is 2, and then x which is 4. If you do this, log base 2 of 4 is 2. So if we just substitute this for 2, we can see that 2 to the power of 2 is 4. And this would work for anything. 9 log 9. Don't know what this number is that I just put, but whatever that is, that's better. So it would equal whatever number I put there. It's the same for anything. If the base is the same as the base here, then it's just going to equal this number. Okay, from now, this is stuff that you might be useful to you and might be interesting to you, but it's not something that we have been taught or that you specifically need to know. E. You might have seen this letter or number technically that we call E. This is called Euler's constant or Euler's constant. Euler, people don't know how to say his name. People say Euler or Euler something. And that is 2.71 something. Oh no, I'll check for you right now. 2.718 to, I don't know, whatever you see. We call that E. And this might seem like a completely random number. Like, what the hell is this? Why would you ever need this? Well, don't you worry, I'm here to explain today. This is gonna get pretty complicated. So, again, this is just out of interest because this is technically to do with logarithms, and you will see this. But you don't need to know where E comes from, but I'll show you what it is anyway. So in maths, we have something called derivatives, which is a gradient function. So if we have y is equal to x squared, I'm just going to do this really quickly because this is not the point of the video. This is what y equals x squared looks like. It looks like this. It won't go negative. That's a mistake. It will always be positive. There we go. Something like that. And let's say we got this graph, and you guys know what gradients are. So if we wanted to find a gradient here, it would be like this. We'll do a tangent and then find a gradient like this. And that'll be the gradient at that point, and you can do that for at any point there. But if we wanted to graph how the gradient changes, we'll find something called dy dx. And this is how the gradient of this function changes. So if we did this real quickly, this one, you can see that it starts negative. If you put a tangent here, you can see it's going down. I deleted it accidentally. It's still going down. Then it reaches 0 here, and then the gradient starts going up. And actually, what's interesting about this, if you graph the gradient, you get a straight line. And let's see what we get here. With this is down here. This is where the gradient is negative, so it's negative down here. I don't know what these numbers are. I'm just making up numbers. This is negative. It's positive. The gradient is negative down here. Then it's 0. Technically, this should be going through the middle like this. So yeah, it goes down. It goes negative. Then it's 0. Then it goes up. Cool. So we're basically graphing how the gradient changes. It gets really complicated. So this right here is probably already pretty complicated, but I'll keep going anyway. So there's a graph of y is equal to 2 to the x. And let's see what this graph looks like actually. Alright, so this is Desmos, guys. This is a graphing calculator. Basically, it allows me to make graphs without me having to draw them, so you guys can see how they look like exactly. Let's go y is equal to 2x, 2 to the power of x. We get this graph. It goes like this, and that's pretty cool. Anyway, so okay, let's see what's the derivative. So what if we graph the gradient of this function? What would we get? That's what they were saying. So let's do that. 2 over x. Oh, look at that. It's pretty similar, wouldn't you say? It's like basically identical. Like the way the graph goes, it looks like a transformation. So, all right, what if we do y is equal to 3x, or 3 to the power of x, sorry. We'll get rid of these ones. We get something that's a little bit forward to the left. And then let's do the derivative of y. Let's do the derivative. This is, by the way, this is derivative notation. You don't need to know this, but this basically means what is the function of the gradient of this function, which makes no sense now I say that out loud. But there we go. You see, it's even closer, but it's on the other side. So there must be some number between 2 and 3 that has the derivative of the function be exactly the same. So we'll call this number e. So e to the x, if you found a derivative of this, would equal e to the x. What this number is actually e. So if by, I think it was trial and error, or they might have done some mathematical way, but we found a number where if you put e to the x and then we do the derivative of e to the x, you can see it is exactly the same. So this is useful for multiple reasons that I'm not going to get into because I've already gone into far too much detail about this. You do not need to know this at all at this moment in time, but I thought this might interest some of you. That number is e to the x, so the derivative of e to the x is just e to the x. So that's what e is. And what are you babbling on about? What has this got to do with logarithms? I just wanted to learn about logarithms. The video title says logarithms. Why are we doing calculus? And that's a good question, honestly. But the reason why we're doing calculus is so I can show you what e is, because you're going to find something called the natural logarithm. The natural logarithm. And the natural logarithm is it's called ln, and that stands for log natural. And you know what this means? This is just a log, the same as any log, but it looks complicated, so they use it to confuse you. And the natural logarithm is just log, but base of e. So that magical number, which derivative is the same as the function itself. That magical number here, but that's basically what it is. So the same rules apply. So ln a plus ln b is equal to ln ab. That's just ab. And it's going to be the same as, if you go back in the video, all the rules are going to be the same. But the only difference is that we're using log and the base is e. So this is asking what power of e do I need to make x? So that's all ln is. And you don't really need to know what ln is. You only need to know that it's logarithm and that it's a logarithm and it uses logarithm rules. I hope this was helpful to you. If you want me to do more videos like this in the future, where I explain topics like this, I'll be happy to. Hopefully, if there's any questions, you can open a help channel in the Discord server of the First Year Discord server, or you can just DM me on Discord, and hopefully I can help you out. But I'm not too smart, so don't rely on me. All right, goodbye, guys.